So in a previous video, we went ahead and took one of these LED cards from the late 70s, and we reverse engineered it, came up with a schematic, which I've got captured here. And from that, we deduced how it worked, and then basically I came up with an interface for it. Just as a quick reminder, we have 4 bits that are the BCD value to be displayed on the LED. We have 3 bits that are the address of the LED from 0 to 5. And then we have an enable where we pulse a 0 to that enable, and that actually writes the BCD value to that position. I've broke out my was it EasyPic5 board here. I've got an 18F4620 I think in it. Yeah, that's what's in it. That happened to be what was in the board when I pulled the board out. I've built up a little wiring harness here. This is actually rather crude, but it works. It's just simply an edge connector that I've soldered a pin header onto the back to get at the control signals, and a bit of a pin header here on the front that just becomes a set of ground pins. And then I found an edge connector in my junk box that I was able to just saw apart that was the proper width here. If I can get it to slide off. It was the proper width here for the power input, and that's just simply bringing power onto the board. There's a couple of reasons to do this on the EasyPic5. This is a 5-volt system on the EasyPic5, so this is all 5 volt. The PIC32 is of course 3.3 volt, so it's not directly compatible with this. Anyhow, I've gone ahead and written a quick bit of C code using the Pro C compiler from Microelectronica. Got it programmed here, and when I power this up, what it'll do is it'll write 543210. Hold that for a bit, and then it'll just start writing an up count. It's going to count from 0 to 65,535, and then roll over. So we should capture this here on power up. They're just writing the test pattern out, and there it goes counting. And so this is working exactly in the scheme here we came up with, where the BCD value is being written on the lower 4 bits, the address of the display from 0 to 5 in here, and then I'm just pulsing the E1 pin low. This is connected directly to a single 8-bit port on the EasyPic5 back there. The port pin out is labeled here. There's bits 0 to 7, the control signal they're hooked to, the color of the wire and the edge connector pin they come off of. I just drew this up to make getting the jumper wires in place nice and easy to do. The PIC processor is running at 20 megahertz, and it'll just sit here and continue to count up. I've tested all 4 of the boards we looked at in the reverse engineering video, and 2 of them have issues. One of them has a dead display. The 7-segment display is just plain dead. Another one has, I think in this column here, a bad decoder. The 4511's bad, but 2 of them work. The LEDs are nice and bright and red, nice and pretty, which I like. You can see here that I'm counting up at an unsigned 16-bit integer, so we passed the 32767. I'll walk through the C code here in a second, how I implemented this. It's kind of brute force-ish. Those are even words, but it works. It's good enough for what I wanted to do here. So anyhow, I'll reposition the camera, and we'll jump in and look at the code. So I thought we'd go ahead and take a look at the source code. It's used to drive the National Semiconductor 7-segment display. I'm using the Micro C Pro for PIC compiler here. I created basically a default project. I picked the PIC18F4620 simply because that's what was on my EasyPic5 development board. The only difference from the standard project is the frequency is 20 megahertz. Again, there was a 20 megahertz crystal plugged into the board from a previous project. So we'll run through the source code really quick here, and hopefully kind of explain how this all works. So, YouTube. It should have been YouTube. Anyhow, this is the ShadowTron blog. You already know that. Let's jump in. So I'm using a single byte on port D to control the 7-segment display. We've talked about this in the reverse engineering video, but these lower 4 bits of that byte contain the BCD value that gets written to the single 7-segment display, the display number to be written to, and there's a clock here, and this is the bit that gets set to a 0 and back to a 1 to actually clock the value in. That's kind of explained here, and that A2, A1, A0 control the display to be written to from the value 5 to the far left to the value 0 to the far right, and DCBA are just simply a BCD value to be displayed from 0 to 9. So this bit pattern here will write a 9 to display position 1, and by taking bit 7 here and pulsing it low and then back to a high, we've written that byte. So how does this work? Let's jump down here into the actual main where we just set up our various registers. The analog inputs are set to digital. We are sitting on port D is what we're actually using to control the display. So it's set to be an output for all 8 bits. I'm toggling the bits on Tris A just to show there's activity, so I get something visual happening on the board. Besides that, it's not used for anything. Initialize the ports, and just to begin, I'm going to write out a 0 to display 0 and a 1 to display 1, 2 to display 2. You saw that when the board powered up, and this is how this is being done. The clock starts at a high, its character position 0, and the BCD value 0. Apologies for Rosie choking off in the background there, or coughing. Hopefully she'll quiet down here. And then we just write a 1 to display 1, 2, 3, 4, 5, 6. Delay a couple of seconds, and we just simply go into a loop. I have a integer counter variable, which was defined way back up here at the top, and initialized to 0 to begin with. So that's happening right here. And all that's going to happen is we're going to display on the displays the value of that variable. We're going to increment it. We're going to toggle all 8 LEDs on port A, and we're just going to sit here in a loop. When this counts up to 65,535, it'll roll over to 0 and start counting again. It's a 16-bit counter. Being a 16-bit binary, it can count from decimal 0 to 65,536. So display integer is called, passing the value of count. Display integer is sitting right here. It gets a integer value passed in. I probably should have put unsigned in there because it is unsigned. I'm creating a little character array that's 7 characters. That'll hold, since there's 6 displays, the 6 positions of the display, and the 7th byte is the null byte to terminate the string. We are taking this value of x and we are writing it to that string variable. We are telling it to do leading zeros, to be 6 wide, to print an unsigned integer, and the value of that integer is x. And so for the value of 0, this will put in the string 0000000 in ASCII. In this example here, if we passed in the value of 2,198, it would put 002198 into the string. Again, these are in ASCII. And from there, we convert the ASCII to BCD, and that's what that little loop right here does. In decimal, the value 48 is the character representation of the number 0. In decimal, 49 is the character representation of the number 1. And so by having an ASCII 0 here, or decimal 48, and subtracting 48 from it, I end up with the binary value 0 here, which is the BCD equivalent of 0. If we take the 2, that's 50 in decimal. We subtract 48, we end up with the binary value of 2, or in this case, the BCD value of 2. So this is how I'm doing the BCD conversion. There's a ton of ways to do this. You'll find lots of resources on the web. This is just a quick and dirty hack I did to make this work. There's some comments here about what we just talked about, taking an ASCII 1, which is equal to decimal 49, subtracting decimal 48 from it, resulting in a value of 1, or the bit pattern 001, which is the BCD of 1. And it's just, I've just said this two different ways. We're going to call this function called writeIt. What writeIt does is set the bit pattern on port D and then toggle this clock bit. So as it says here, each call sets clock to a 1 initially, which is that bit right there, represented by the CK. Sets the position I want to display to in these 3 bits. So there's display 0, display 1, display 2, all the way to display 5. Sets the BCD bits to 0, then adds to it the BCD conversion we created here to it. So if this was going to output, say, the BCD value for 8, we would have ended up with this pattern right here, 100, in strings of 5. Actually, it's containing 0000. This is, or let me say that again. It contains the bit pattern 00001000. By adding that to this value, what we've done is, in this case, we would have added that 1 right there to set up the BCD value. We do this for all 6 positions. We call writeIt. All writeIt does is say set port D equal to that bit pattern. Take bit 7 low, take bit 7 back high. That produces the clock and writes the value to the physical display. So that's really all there is in the code here. Yeah, you can comment all day long on the quality or the lack of quality or the approach I took. That's really tangential to what I wanted to really talk to here. Was just really more, a quick and dirty method of getting the values. In this case, the values where I'm counting up onto the displays. You saw that running in the first half of the video where it was doing the up count. And this is really, as you can see, there's more comments here than there is code. Just defining the control byte format, etc. So no real magic here besides kind of the bizarre way here I have done the BCD conversion. Again, it's really only 4 lines of code. I will say the downside of this approach is you must have in the library manager SPRINTF library enabled, which chews up a fair amount of room. And apparently the C-type and conversions library also gets selected. Maybe when SPRINTF was selected, I don't remember enabling these myself. Yeah, those must have been enabled automatically. Or maybe not, I don't know. Anyhow, this SPRINTF method occupies a fair amount of memory where SPRINTF is implemented. Typically in my projects, I am using SPRINTF to create debug strings and sending them out of serial port, so I typically have this included in the project. For something small like this, it's absolutely fine. This could, of course, be expanded to have perhaps a real-time clock calendar module that the PIC read and put the time out, whatever it wanted to be. But I think that's enough talking about the code here. Anyhow, I think I'll wrap this up here, and we'll talk soon. Bye.